on now?
That's great, thanks.
Okay. So today we want to think about the case where nu is a fraction. Okay, so what does that mean? So there are n5. Let's just think about nu being less than 1 for a moment. So there are n5 states in degenerate states in the lowest Landau level, and if n is lesser than n5, you see that there are a huge number of degenerate many-body states, which are all potential ground states. Right? So if I imagined doing degenerate perturbation theory in any perturbation, you see that I have like a massively hard problem. This n5 choose n, where if I replace n by nu times n phi, for fixed nu and large n phi, you see this is going to scale exponentially with n phi. There's loads and loads of states. And in general, I have a very hard problem because I have all these degenerate states, and any perturbation is going to split them. Right? So in particular, interactions, which we didn't pay that much attention to yesterday. So the Coulomb interaction, which is on this scale, yesterday we ignored it because we were studying physics at or near integer fillings. And then we saw that there was a gap to single particle excitation set by h bar omega c. And then we said, because this potential energy was much, much less than h bar omega c, we didn't think about interactions in the integer quantum Hall effect. However, today,
excuse me, so
potential energy, yeah.
E squared divided by LB. I thought that potential energy means that in the denominator you have the characteristic distance between the particles, right?
Right, but so at or near fillings 1 or 2, the characteristic distance between the particles itself is set by the magnetic length. So yeah, so maybe I should write that. The characteristic distance of particles itself, the order of magnetic length, because nu here tells me I have as many number of particles as flux quanta. Remember, flux quantum is the amount of flux enclosed by a circle, roughly by a circle of area, the magnetic length. And so if I have as many number as electrons as flux quanta, I have roughly an electron for a magnetic length, and so the interparticle spacing is set by the same length. Okay, and so this energy is much smaller than that in the when the magnetic field was going to infinity, so in the strong magnetic field limit. And so we said we can forget about it for the integer quantum Hall effect. Yeah.
What is that notation that you have? There's the interaction not
important.
Oh, okay.
Is this not like universal notation for important? Okay, that's important. Yeah, soon it'll be like important equals no. Okay. But today, because of this large degeneracy when nu is a fraction, on the other side we basically have 0, and you see that interactions is everything. So the entire problem we're going to be thinking about today is how does the interactions between electrons split this massive degeneracy in the ground state space and give you a surprise, surprise, unique ground state with a gap. Okay. So to do this, let's actually change the gauge that we work in. So thus far, we were working in the Landau gauge. Plus B, which is this. And this was a nice gauge to work in for what we did so far because there was translation invariance preserved in one direction in this gauge. For what we're doing today, it's better to preserve rotational invariance. and that's a different gauge, and it's called the symmetric gauge. And in both cases, there's a magnetic field in the z direction. Note that actually this choice means the magnetic field is in the minus b direction. And it's just for notational simplicity for what comes after. Here, though, the magnetic field was be in the z directions. OK. So in this gauge, you see, instead of translation invariance, what we have is rotational invariance, because the vector potential, now looking the view from top, where this is the xy plane, the vector potential you see is in the theta hat direction. Right? And so there's rotational invariance in the problem, and it's still exactly solvable. And the eigenfunctions in this gauge are parameterized by an integer m. Okay, so m is an integer. And z is x plus iy. Yeah?
So when you're considering the symmetric gauge in this case, you're assuming that you don't have boundaries, right?
I'm assuming I don't have a boundary at the moment again. So it's similar in spirit to solving the problem in the Landau gauge, infinite
Right.
Landau.
So in this case, how would you define the filling fraction? Because in this case, the area of your sample is infinite.
No, so I can, so at the moment I'm only solving the single electron problem, okay? When I fill this, so just hold your thought for a minute. I will then discuss the many, you're asking a question about the many electron wave functions.
Right. I mean, if, just taking what you wrote after,
Yeah.
filling fraction is the number of electrons over n pi, and
Yeah.
pi is proportional to the area. So in this case, if you want to preserve the rotational symmetry, you have to consider infinite.
So there's an equivalent definition for nu locally, which is the number, so I'll write it as, it's not the total, it's the number of electrons per flux quantum. Okay? So this I can define locally. Is this 1? Is it 1/3, 2/3? So this doesn't, the reason this is the same as that is because I'm talking about liquid states and they have the uniform density everywhere. So an extensive definition like that becomes an intensive definition like this. So I can still talk about it even even with edges and with a finite sample. Okay. But these are the single particle orbitals. Okay, and m here has the interpretation of being the angular momentum. So this is equal to the angular momentum over h bar. Okay, so pictorially, what these wave functions look like, if I plotted mod psi squared in the xy plane, they have maximum weight on a ring. So I'm plotting mod phi m squared. The radius of this ring, Rm, is square root 2m times the magnetic length Lb. And the area of this ring is pi Rm squared, which is 2 pi Lb squared times m. Okay, so just like we saw in the Landau gauge, the counting of the states is the same in that we have one state for every flux quantum. Right? So the state m encloses area m times 2 pi lb squared. So if I divided that by m, because there are m states within this ring, I find that I have one state for 2 pi lb squared. So same counting as in the previous gauge. And this has to be, because remember, just different gauge choices are just different bases to express the same spectrum. We have the same spectrum as we had up there. The only difference is by choosing a different gauge, each of our eigenfunctions is some linear combination of the original states in the Landau gauge, but in the same Landau level. Okay, so spectrum does not change when we change the gauge. Okay.
Can I ask? So classically, you have the same D,
Yeah.
then you have the same solution. But quantum mechanics, if you change A,
Yeah.
then some quantum mechanical effects, right?
No, so if you change A, indeed the Hamiltonian changes, but what is invariant is the spectrum. Because the energy spectrum only cares about the physical magnetic field, and a gauge transformation is, if you wish, is a coordinate transformation, right? So the energy spectrum cannot change if you change your gauge. The wave functions can become linear combinations of what they were before, but the spectrum can never change. I think this is true even quantum mechanically. There's no observable effect of the gauge choice.
Well, there are effects like a Harmon effect, whatever, but they are probably so different topology you have, or?
Arnold-Bohm effect are phases that are picked up in the wave function, right? So
So this can happen here as well, or not really?
no, so what I believe is true is that I can take these wave functions that I have here in, so by the way, sorry, these are the wave functions only in the lowest Landau level. I haven't written the ones in the higher Landau levels because we're not going to use them. So I believe I can take these wave functions, and take an appropriate linear combination of them, and make every single Landau wave function. So in that sense, all I've done is rewrite the problem in the lowest Landau level. Okay. So just another observation. The difference in the radii of adjacent wave functions, so Rm plus 1 minus Rm, you see that in the limit of very large angular momentum. So the larger the angular momentum, the farther the ring is from the center here. But the difference between the radii of adjacent states scales as basically 1 over square root of m. So it goes to 0. Okay, so once again, in this gauge, as you go further and further away, the wave functions will be dramatically overlapping with one another. Okay. So we have a description of the lowest Landau level in this gauge. And now these are the single particle wave functions, and now let's ask ourselves, when we put in n electrons, what do the many body wave functions look like? Okay, so there's one very important fact about the lowest Landau level, which is that any many body wave function that you can write in the lowest Landau level has to be of this form. Okay, so any linear combination that I pick of these phi sub n's for a single electron has this Gaussian factor up front and is some polynomial in these in the z sub m, right? And so therefore it's only a function of z. It's some function fn of z. Sorry, f1 of z, so 1 electron. And what this means for n electrons is that psi of z1 to zn, so it's now an L electron wave function, is some analytic function of, analytic, actually antisymmetric function of z1 to zn times ci squared over 4. Where I'm sorry, I've now normalized the z, which is why there are no units here in the bottom. Okay, so this is this crystal clear to everyone? This is the form of any wave function I can write down, any number of particles that lives in the lowest Landau level alone. Okay, so I'm going to exploit this fact to guess wave functions that are at the correct filling in the fractional case. So let's first write down what the wave function is in the integer case. Okay, and now here by nu is equal to 1, I mean that I fill, if I have n electrons, what I do is I fill the states, m goes from 0 to n minus 1, right? And this creates some circular droplet for me. And locally, I have 1 electron per flux quantum. Okay, so there is an edge in this, but I don't care at the moment. So this is a well-defined state. In fact, by saying I fill these orbitals, I can write down what the wave function is. So sine of z1 to zn is the anti-symmetrized version of this product. So I take electron 1, put it in m is equal to 0, electron 2 in m is equal to 1, electron n in m is equal to n minus 1, anti-symmetrize the whole thing over the labels of the electrons, and multiply it by this Gaussian factor, right? So this is just first quantized fermionic wave functions, anti-symmetrized because I have fermions. Okay, so this is equivalent to this guy, which is n minus 1 times the Gaussian factor. And it turns out is also exactly equal to this. Okay, so just to sanity check, when a particle I and j are in the same position, this wave function vanishes. That means it's the same thing as setting 2 rows in the determinant equal. Determinant vanishes, anti-symmetrization product vanishes. The highest power of zi in here is zi to the power n minus 1. And that's great because that would be the highest, that would also be the highest power here because we only occupy up to n minus 1 orbitals. Will also be the same thing to determine. And I encourage you, if you've not done this before, to show that these two are equal, that this is the same as that. Okay, so that's nice. We've written down an explicit wave function for the integer quantum Hall state that we were studying yesterday. And so, for example, if we now calculated what the density, which is the expectation value of psi I dagger psi I in this state. N is, right? So then we see that, maybe I shouldn't take it off. Let me say that this is equal to that. So if I plot this density versus radius, so I add up this is at position I, so I could call this at position I vector. And I add up the density within a shell of radius r. So then I'll find this profile. So the density is 1 per flux quantum here. And then it falls off to 0 basically at the radius of the n-1th orbital. And it has width, it'll be here. Okay, so everyone sees that what I've created by filling these first n-1 angular momentum orbitals is it's almost a uniform density droplet up to some radius set by the number of electrons I have. This is kind of where corresponding to the maximum value of m, the radius corresponding to the maximum value of m is, and then the density drops. Okay, so this is I've created a liquid state because the density is independent of position up to the edge. Yeah, so you see that it's a circular droplet, right? Okay, yeah.
When you write this psi I dagger psi I, you're meaning creation and annihilation operators in the Fock space.
In the Fock space, yeah.
Right.
Yeah.
But written in the position space.
Yeah, that's right. Okay. And finally, this form of the wave function also lets us understand what the excitations to this state look like. So in the energy spectrum, so now I should draw the energy spectrum versus m, the angular momentum. I still have a flat Landau level. And so the state that I wrote down there is, if you wish, I filled in m going, so actually, sorry, m is always positive. So I should only draw it this way. I filled those electronic states from m goes to 0 to m goes to n-1, right? And what I've imagined is that basically I fill only these number of states because after this, like the problem that you guys solved yesterday, there is a confining potential, so these Landau levels go up. Okay? So yesterday, the problem that you solved was for Landau levels in the presence of an electric field, and you discovered that the Landau levels get tilted when there is a linear potential. And so I fill those states up to when I hit the linear potential, let's say. And so these are empty, these are all full. Okay, and now an excitation from this state, which is one I wrote down there, involves taking away an electron from here and promoting it to the next Landau level, right? So this is a hole in the lowest Landau level and a particle in the higher Landau level. And in terms of density, what this will look like if I actually just remove one electron first, I'll just see a dip in the density corresponding to the value of, at the radius corresponding to the value of m at which I removed an electron. Yeah? Okay, so this is what excitations about the droplet looks like. What it does is basically it creates holes in the density, in the charge density, because you remove electrons from specific points here at radius squared m0. Okay, so in this gauge, we understand what the integer states look like. So now let's start to think about the fractional values of nu, which was our original goal. Okay, so we now want to understand what are known as the Laughlin states. which occur at mu is 1 over m. I'm sorry, m is also the angular momentum, and it's also related to the filling. M here is 1 is the integer case, and these are all fractional. Okay, so the Laughlin states are candidate wave functions. We're going to write them down for the ground state of the interacting problem of electrons in a strong magnetic field at these values of local filling. Okay? So here was Laughlin's just inspired guess, which is that, remember, psi n of Zi was I'm this Gaussian. We said that this is an analytic function of all the Zi's, and Laughlin just guessed that this analytic function is the integer quantum Hall wave function raised to the power m. Okay, so let me box it so you can see. So this is the guess for the many-body wave function at filling mu is 1 over m. Okay, so let's now go through and convince ourselves that this is the right answer. It has the right properties that Laughlin claims it has. You know, for example, we need to check, is it a liquid state? We're trying to explain the quantum Hall states are liquid states in that their density is uniform up to when you reach the edge, right? So we need to first show that this has a uniform density. Then we need to show that its sigma xx is 0. Then we need to show that it's an incompressible state, that it's truly the ground state of some, if not the Coulomb interacting potential, at least of some interacting potential at this filling. Right, so we have a number of properties to show, and so let's go through and convince ourselves that this is the right answer. Okay. To do this, there's a nice analogy due to Laughlin, known as the Laughlin's plasma analogy. Yeah.
So the Laughlin state is just like a trial function for the ground state, but we're assuming here that that ground state is unique, that there's no degeneracy, right?
Yeah. So this is you can work with this wave function and find out that there will be degeneracies depending on the topology. But for the moment, to avoid that issue, if you wish, and this is how people do it numerically too, let's assume you work on a sphere. A sphere is a closed manifold, so there's no issues of edges, and the ground state will be unique if you, and there's no topological degeneracy, etc. Right.
And so you're constructing the wave function from the plane, right?
Okay, so the wave function I done is for the plane. I can write down the wave function of the sphere too. There is a
even though in the plane the Landau levels are infinite degenerate,
yeah.
in the sphere they're finite degenerate.
Yes, you can still write down the exact wave function of Laughlin
Sure. So, okay.
on the sphere.
So what you're saying is that I can map the states from the plane into the sphere, right?
Well, no. So there are different geometries on this. On the plane, what we're creating, this state looks like it's a circular droplet of some radius, right? And it has an edge. On the sphere, there's no edge. It's just a uniform droplet on the sphere. So you can write down the exact wave function in both cases. The physics is different at the edge here versus there. However, the bulk physics, which is what we'll be talking about, is the same. So, yeah, That's maybe the. I don't want to. It's not true that you can map the entire global problem of the sphere onto the plane. You can locally map the regions, the North Pole to look like the sphere plane, etc. Okay. Yeah.
So, like, the lasting state is the ground state of the case when you have like a weak magnetic field, right? So this when interaction is strong, which means the magnetic field is.
No, it's the ground state in. So it's a ground state that lives entirely in the lowest Landau level. So if you wish, I've taken the order of limits that the magnetic field is so strong that I don't have to worry about the higher Landau levels. And so the only like if you wish, the effective Hamiltonian is, you can write it as a projector onto each of these states M times the interaction between particles. Ri, I less than j. Okay? So this is actually the problem we're trying to solve. What we're doing is, we know we had the problem of electrons plus interactions plus magnetic field. We first solved the problem of electrons without interactions and strong magnetic field. We say magnetic field is super strong. We're not interested in the energies at this scale. Instead, we're interested, because we're the filling fractions, we're looking at keep you within the lowest, can keep you within the lowest Landau level. We're effectively solving a problem just in the lowest Landau level of the interactions. So if it's the opposite, it's in the really strong magnetic field limit that you would hope this is true.
So like the difference between like integral fundamental state and fractional fundamental state is that so those states have very strong magnetic field, and then this issue that we only consider the lowest Landau level, and then like for integer we have weak interaction between the electrons, but in the fractional we have a strong interaction.
No, it's more that we have the same interactions between electrons. In the integer case, they only perturb weakly around the non-interacting state because interactions will have to cause electrons in here to jump up to the higher Landau level, right? So if you thought about particle hole excitations here, the way it has to dress it is to excite electrons up there. And this scale is big. So interactions are not able to perturb the integer state by much. But in a fractional state where I have lots of such holes in the Landau level, the interaction, because these states are all degenerate, of course the interactions can split them. So it's not that I'm making the interactions strong or weak. It's that the filling factor nu tells me that for the integer case, interactions will only perturb weakly as long as their strength is less than this h bar omega c. For the fractional case, it doesn't matter how weak I make the interactions, they will always determine the physics. Does that make sense? Okay. So back to that wave function and its properties. So Laughlin's plasma analogy says, look at mod psi z squared. To the mod 2m and pretend that this is the weight in a partition function in StatMech. Right, so quantum mechanically, this quantity has an interpretation as the norm of the wave function. I just take its mod square and integrate over all the particles. But pretend for a moment that this quantity is the partition function that you would write down in statistical mechanics, which is, so in statistical mechanics, if I had n particles, I would write down some partition function like this, right? So pretend this is this. If you pretend that's true, you can ask, what is this U classical? What is this classical energy between these fake particles Z1 to Zn that has the same properties as the norm in my quantum wave function? Okay, so all this needs you to do is to take this thing here and say if it's equal to e to the minus beta U classical, you take the logarithm divided by beta, and you say that for this to equal that, the classical U has to be this. Okay, so at this point, I've done nothing but identify this with this. Okay, but this fake classical energy has an interpretation in its own right. And the interpretation is that it's the potential energy of a classical plasma. In 2D. So let's see why. So first off, the electrostatics is different in 2 dimensions. Which is easily seen by thinking about Gauss's law. So you know that Gauss's law is integral E dot dr is Q times 2 pi. And so if the electric field of a free charge is Q over r hat, then the associated potential energy actually scales logarithmically with the distance, right? So unlike 3 dimensions where forces of 1 over r lead to, the force is 1 over r squared and the potential is 1 over r. In 2 dimensions, electrostatics leads to electric fields which go 1 over r and potentials that go logarithmically with the distance. Okay, R0 here is it's some constant factor that will not affect any of the physics because it just shifts the potential by a constant amount. Okay? So it doesn't matter what it is. And so what this tells you is that in 2 dimensions, charges interact with logarithmic potential energy. Okay? So that is already hopefully a clue for where this log comes from up there. So let's just see that. So the first term, which is U0, is m squared summed over I less than j. This is clearly the interaction in 2 dimensions between charges with charge m. Right? Does everyone see this? Each charge will create, from that formula up there, each charge will create a potential U, which is minus m log r minus zi over r0. So the particle is at zi, and this is a potential created by charge m at a distance r. And at that distance r, this is the potential energy between a second charge of charge m and the first one. Okay, so this bit is interaction energy between charges with charge m. What about the second term that we have out there, this m over 4 summed over all k mod zk squared? To understand that, note the following. So that term is u1, which is this guy. So first notice that the gradient square over m of, or actually let's just do this. Because, sorry, this was because I remember I defined z as the dimensionless ratio of x plus I y over LB. And so when I just plug this in, I find that that's where I get this 1 over LB square factor. Okay, so this is just differentiating mod z squared. But also note that if I take the potential u created by a charge, I can write this as minus grad square u2 divided by m is right. So by Gauss's law, or I guess this is the Laplacian of a potential will give me the charge density in that area, right? So I have this formula that the Laplacian of mod z squared over 4 gives me some number, but I also know in 2D that the Laplacian of the potential gives me the Laplacian of potential gives me a charge density in the area. And so identifying the potential with mod z squared over 4, I find that mod z squared over 4 would be the potential created by a charge density rho b given by minus 1 over 2 pi LB squared. Is this clear? So what I'm interpreting the second term as is that it's the potential created by a uniform density of negative charge, that's the minus sign here, with this value. Okay, so now we have a full picture for what this 2D classical gas is. So, which is that we have a uniform background of negative charge, rho sub b, which is given by this. And in it, we have positive charges, each one with charge m, floating around and interacting by electrostatic energy. Right? So this is the plasma with the same partition function as mod psi squared of our Laufin wave function.
So here the background confining potential appears naturally in this analogy. But for example, if I consider just a system of electrons, where are we not considering the effective Hamiltonian a background potential as well? Because physically I cannot put a lot of electrons in a zone and assume that they're confined, right? Because of the repulsion, they'll tend to go outside.
No, so this thing here is not appearing because of the background potential in our.
No, right.
Yeah.
Okay, I can see this in here, but if I want to treat this problem over here,
yeah,
for you to have the lovely droplet,
yeah,
you should
there is
have
some background.
background.
There is some background there. Yeah.
Okay. However, if I plug this background in the Hamiltonian as an effective potential, that will affect my wave function.
It will affect. Okay, I'll answer this later. It will affect your wave functions, but for the moment, assume that the background potential is there indeed to neutralize charge for the droplet, for the electron droplet. But for the sake of the Hamiltonian, the only thing we consider is electron-electron interaction. Right? Just assume that for a moment. Okay. Nevertheless, in the fake classical plasma, we have a negative background with positive charges, each of charge m floating around, and these are now all classical, right? This is just a gas of them. Okay, so why is this analogy useful? Well, because it turns out we know a lot about classical gases, classical plasmas. So for example, one thing we know is that the Coulomb force in 2D is very long range, right? So we saw that the potential energy between any two charges m increases logarithmically with the distance between them. So the system is very, very unhappy to have net charge in it. Like it dislikes having a net charge of, I don't know, plus q and minus q. This is energetically prohibitive because of the amount of energy paid by the system to do this. So this tells us that locally there should be neutrality of charge. So that the density of these m particles, let me call that small n, times the charge m, plus the density of the background has to be 0. Okay, so this condition tells me what the density of my m particles is, which by plugging in is this, which is a boxed result for us because this is the density of electrons in the Laughlin state. Right? Because the z sub I were our actual electrons in the wave function that Laughlin wrote down, and we've now said that the density of those particles is this, and so this is the actual density of electrons in the wave function that we wrote down. Okay, so that's a boxed result and gives us the correct filling factor, which we can see by plugging into this formula. So this is density by 0. Plug in for small n, and remember the flux quantum phi 0 is hc over e. Everything cancels, and you're left just with 1 over m. Okay? So we've discovered that the wave function that we wrote down magically corresponds to the density of electrons such that there's 1 electron for every m flux quanta. Okay? And remember, m is odd here. So we have candidate wave functions for fractions 1/3, 1/5, 1/7, and so on. Okay, so that's great. At least our wave function has the correct filling fraction. Okay, so let's check its more properties of it. So second property is to ask, does it correspond to a liquid-like wave function? Remember, the quantum Hall fluid, they're all fluids. That is to say, they're completely translationally invariant. You can't tell one spot from another except for the edges. And so the density of that wave function better be uniform. And the plasma analogy actually tells us that it is uniform because the density of these m particles are controlled by the background density, which is uniform. And so the m particles themselves have a uniform density in the bulk. When you reach an edge, they actually do something like this. Where, again, all these features at the edge are at the scale of the magnetic length. Okay? Okay, so that's good. So right filling factor, it's a liquid-like state. What else can we say about it? Any questions so far, or so far so good? Okay, so the other properties that we just can directly infer from the plasma analogy is that this is a state with short-range solid-like order. But at long distances, it's a liquid. So what do we mean by this? At really short distances in the plasma, the M particles repel, right? So they don't like to approach each other. The distance between them has some value because there's a strong repulsive force if they come too close. So if I went in and looked into the structure of that wave functions, I'll find that at very short distances, the electrons avoid each other. And at longer distances, it looks like a liquid. You don't see the fact, the difference between solid-like order and liquid-like order is if the electrons formed a solid, they would literally be stuck in a crystalline form. Okay? So that's not true. However, at short distances, it looks something like this. It's very rigid. The electrons avoid one another. However, at long distances, this crystalline either is lost, and the electrons are more randomly placed with respect to that crystal. So that's one property, and in some sense, it had to be this way because if remember in our Hartree-Fock calculation as well, we saw that whenever the spins being anti-parallel was not preferred, that is, the Hartree-Fock calculation preferred that the spins be aligned because that naturally meant that the electrons avoided one another. So always the biggest cost in interactions is at short distances, do the electrons avoid one another? If they do, then you automatically have a good wave function to try to describe a ground state of an interacting problem. Okay, so at least this has those properties. That's good. Then what about the compressibility? Which is secretly a statement about sigma xx. So compressibility, remember, was defined as the change in density and changing the chemical potential. Okay, so in our metal on lecture 1, we said that this was equal to the density of states metallic. Everyone remembers this? This is just the compressibility. We just plugged in. It came out to be exactly equal to the density of states in the Fermi energy. However, here, a slight change in chemical potential, when we change the chemical potential slightly, you cannot change the number of electrons in the region infinitesimally because, like we said, because of the long-range forces in the plasma, right? So let me just pictorially tell you what that is again. When you change the density of the M particles by a little bit, you're not changing the background density. So rho b is still minus 1 over 2 pi lb squared. But the density of the M particles in here, instead of it being the magic small n that we have there, what you're doing is you're increasing the density to n plus delta n. Okay? So when you do that, clearly you pay a huge cost because the net charge is not 0 anymore. And so it's not possible with an infinitesimal amount of energy to change, change chemical potential by a little bit. You cannot change the density by a little bit because you have to pay a lot of energy. And so this is actually 0 for the Laughlin state. Okay? So it's an incompressible fluid. To add an extra electron or to remove an electron, you have to pay a finite amount of energy cost, not an infinitesimal amount of energy cost. In our metal, it was infinitesimal because we had a Fermi surface. We could add an electron arbitrarily close to the Fermi surface. That's this. Here we can't. It's of finite energy cost. Okay, so that's where this big difference is coming in. And this is directly related to what sigma xx is in these two cases. Okay, so fourth is that the Laughlin state has a gap to all excitations. Yeah. So, which is where this is coming from. And so we've found a unique state. I'm not proving this. I'm kind of stating the properties now of the wave function we wrote down. The Laughlin wave function is a unique ground state that we have found on the sphere for the moment before you. And to excite it in any way, we need an order 1 amount of energy. Yeah.
Wait, but if I consider this picture of the Laughlin droplet, right? I know that is incompressible. However, I can deform the surface of the droplet if I conserve the area, and that's a gapless excitation, right?
And that's an edge excitation. So it's a gap. There's a gap in the bulk. So to remove a particle from the bulk or to add one in the bulk, I need to pay a finite amount of energy. However, indeed, as you said, it's gapless at the edge. Yeah. Which is why it's useful to have two geometries in mind, sphere and disk. On the sphere, it's a genuinely gapped system. On the edge, you'll see, on the disk, you'll indeed see that there are gapless excitations associated with the edge. Okay, another way to see this gap is to actually go back to the wave function and note that the total angular momentum, which is the maximum power of zi in that wave function, right, is m times n times n minus 1 over 2. It's the degree of that polynomial. This is the degree of the polynomial that we wrote down. That's zi minus zj to the power m. And so compressing the droplet basically reduces the total angular momentum, right? That's clear because we had that picture there that greater the angular momentum, greater the radius. So if you compress the droplet uniformly, you're decreasing the total angular momentum of the droplet. If you decrease the total angular momentum of the droplet, and you go back and look at the wave function fn zi, which was zi minus zj to the power m, you see that what you'd have to do is you'd have to bring electrons closer to one another such that instead of this power being zi minus zj to the power m, it's got to go down, right? You see, so if I want the degree of a polynomial to decrease, I'm going to have to decrease some of the powers in its terms. That's what I'm saying. And this costs energy because you can, back in the plasma analogy, it means you're bringing the electrons closer than rho b locally. Okay? So there's multiple ways to see it, but basically what you're doing is when you compress it, you decrease the total angular momentum. The electron gases are extremely unhappy with this because the electrons are not able to avoid each other as much as they did before, and this costs energy. Okay, I now want to talk about the excitations, which is where the fractional stuff comes in. Maybe I'll erase that. So for the integer case, we argued that removing an electron from the Landau level just looks like you make a charge instead of there being a uniform minus E charge, there's now there's a hole of charge plus E. Similarly, in the Laughlin wave function, there is a quasi-hole wave function that you can create. So G plus. Okay, so this is the Laughlin wave function, Laughlin ground state wave function that we wrote down before. Maybe I had of n particle wave function at filling factor 1 over m. And I multiply it by a factor, which is zj minus z. Z is a parameter for this wave function. And if you now go back through the plasma analogy, you'll see that this term adds an extra mod psi z plus squared. Looks like the classical problem we discussed before with an extra term. And this extra term v it looks like that they're at the position z in the classical plasma. There is an extra particle of charge 1. Okay, so the new wave function with this extra factor has the same neutralizing background rho b, has charge m particles moving around, but at position z, which is here, there is a charge 1 particle. Okay, so this is a candidate quasi-hole, yeah.
Charge 1 over n, right?
No, it's in the plasma analogy, it's charge m because this is the interaction between a charge 1 object and a charge m object. Right, so before the other term was m squared because it was.
Sure. But so you're multiplying only by this factor of set j minus set, which in the exponential comes with the logarithm of minus 1, right? So if you want to factorize the m.
Oh, okay. Sorry. I should have said this before. The beta itself is m dependent in making this analogy. Is that what you mean?
No.
But that'll give me the right factor of m times 1 over m, and it'll give me back.
Okay.
Yeah. Sorry, I should have said this before too. Beta, the parameter here which sets the temperature of the classical plasma, itself is set by m, and it's given by 2 over m. Okay, so in my plasma, I've now added a charge 1 particle. It doesn't move, right? Z here is, we don't integrate over z. It's just some parameter. And so there's a fixed charge stuck to this position z. Now the charge neutrality arguments that I ran before will tell you that in this region, right, if I look anywhere around this, in a region enclosing this extra particle that I've added, I'll find that the positive charge 1 repels the electron so that there's 1 over m less of an electron in this region. Does everyone see that? Because I've added charge 1. So for charge neutrality, each electron carries charge m. So I need 1 over m less of an electron because of this. And so that actually tells me what the charge of the quasi-hole is. Okay, so an excitation about the Laughlin fluid, which looks like this, looks like an elementary charge with a fraction of the electronic charge. Okay, so that's one another reason why this is the fractional quantum Hall effect, the quasi-Hall and similarly the quasi-particle-like excitations about the background fluid of the Laughlin-Hall state have fractional charge. So locally, if I went and measured charge, instead of me measuring a charge E, which is what I would think because I have an electronic problem with electrons at charge E, I instead find that locally the charge is only depleted by E over M. So it's a fraction, right? And this is, it's a fractional charge in that. So imagine I have this sample, and I try to put in an electron. Okay, so I give it enough energy, and I have an electronic wave packet here, charge E, and I try to put it into the sample. What I'll find is that it splits into, let me pick the simplest example of M is equal to 3. I'll find that it splits into 3 bumps, each with charge E over 3. Okay, so the element, they will always, in any given sample, because after all my sample is made of electrons, there'll always be 3 of them if they're there, so that the total charge is always an integer. I'm not claiming that I've made total charge, which is a fraction. However, the excitations, instead of carrying charge E, they always break up so that it looks like single particles that carry charge E over 3. Okay, and the reason this happens is because the background fluid of it's a complicated fluid of electrons, and the correlated system of electrons, they create these effective depletion of charges which look like E over 3. Yeah?
Experimentally, how can you tell the difference between one charge E and 3 particles of charge
E over 3. So, so it's been seen experimentally, right? And the way they do it is through short noise experiments. So when you're measuring fluctuations in current, when you try to push in a current of these, the fluctuations in current in that formula, there's actually the charge of, in it appears what the charge of the carriers are. So they actually measure that in these fluctuations, the charge of the carriers is E over 3, not E. Okay, so it really looks like the units that are moving around carrying your charge are made of E over 3. And in some sense, you know, it's like the reverse of what you learn in high energy, because usually in high energy you say, okay, there's a proton at room temperatures, but when I go to really high energies, it breaks up, right, to quarks. And here we're kind of saying the opposite, which is at really high energies we have an electron, right? That's where our UV theory has electrons in it. But when we come back to low energies, we have fractional. We have quarks, if you wish, because they're fractions of an electron, and they have charge E over 3 at low energies. Right? That is to say that if you warm the sample up and you keep doing short noise, eventually you'll find that it goes up to E. Your charge carriers become E again. That's the high energy physics. You come back down to low energies and charge carriers go back to being E over 3. Okay. What shall I do? Okay, so in the last few minutes, I want to go through an argument known as a flux threading argument that actually gives us one more important property about these quasi-holes and quasi-particles, which is that they bind flux. Okay, and those two ingredients together will tell us that these are not fermions, not bosons, but anyons, which are weirder particles. So let me try to do it as fast as I can. So let's imagine starting with the sphere geometry that I briefly alluded to, so that we won't have edges and other kinds of issues. And now let's imagine a thought experiment, okay? And so by the way, by saying the sphere geometry, I mean my electrons live on the surface of a sphere, and the magnetic field is actually radial, right? Because we want a magnetic field perpendicular to the surface, and on a sphere, that means the magnetic field is radial. Okay, so this is my original system. I prepare it at this filling fraction in the ground state. And now I imagine drilling in a tiny, tiny hole and putting in an infinitely thin solenoid. Okay? So this is my solenoid. It's carrying some current. And this lets me tune the flux through this solenoid as a function of time. And I'm now going to ask what happens as I tune this flux really, really slowly with respect to what? Well, we argued that the Laughlin state has a gap to all local excitations. So anything that you want to excite the system locally, you need to give order 1 energy. So as long as I'm going slower with respect to, so let me call that gap delta. And as long as the rate at which I'm going is slower than h bar over delta, I can argue that things are adiabatic in that I'm locally following what the ground state's doing. Okay? So this is a classic trick which we use all the time. And so the rate is smaller than, the rate should be smaller than delta of h bar, so that the time scale, the time you take to do this, is much, much bigger than h bar over delta. Yes, okay. And so phi of t over this really long time scale is going from 0 to a flux quantum phi 0. That's my experiment. Okay, and I now want to describe what happens as I do this. Okay, so first, when you change a flux in time, you know there's Faraday's law. And so Faraday's law tells you that there's an induced electric field whenever there is a changing flux, dt, right? Okay, so changing the flux, let's focus on the North Pole for a minute, and then the same story will apply to the South Pole. So near the North Pole, zooming in on it, looking from above, here is my solenoid, and the changing flux through it induces an electric field that's going to be tangential. Okay, so this is the electric field given by this formula. And the electric field itself induces a current through, and the conductivity tells me what the relationship is between them. Okay, so changing flux induces electric field causes a current to flow, and because I know that rho xx is 0 in this system, it's going to cause a current to flow that's perpendicular to it. So net result of this is that there's going to be current flowing radially inward. This is, use another color. These guys are the current, J. And so when I plug this equation into that one, I actually get an equation for the total current flowing into this region, right? So let me just write down some final equations. d phi dt. Q is now the total charge within this region. So integrating in time, I find that the total charge, once I have increased my phi from 0 to phi naught over some really long time scale, tau, doesn't matter how long I took because I have a time derivative on each side. And in the end, I'm going to find that the total charge is 1 over c sigma xy times phi 0. And using the fact that sigma xy is quantized in the Laughton system, I get h over e times, sorry, plugging this in and then plugging in sigma xy is nu e square over h, I get that this is nu e. Okay, so sorry, just backing up a little bit. The idea was we inserted one flux quantum over a long period of time into our Laughton state. We used Faraday's law in conjunction with the known transport response for this system, which is that it has no rho xx, only has rho xy, induces currents perpendicular to the electric field, and derived that in this process, we would have created a charge Q in this region equal to nu times E. Okay? That's what this whole result tells us. Okay. But there's this value phi 0 is special. Okay? And it's special because inserting a flux phi naught actually has no physical consequences on the system because it's invisible to the electrons. Yeah.
So if I introduce a quantum of the magnetic quantum flux here, it's equivalent to create a quasi-pole, right?
That's what I'm going to say, yeah.
Okay, but in this case, if I introduce the quasi-pole in that sense, then the degree of my polynomial is growing, right?
No, so, okay, then before I finish, let me tell you. While at the North Pole I pushed out charge, the equivalent thing at the South Pole is that charges come in. So, which is to say, right, I've ended up with something with charge nu he here and minus nu e here. So I've created a whole quasi electron pair, and that keeps the degree the same.
Oh, okay.
So I didn't write down the wave function for the quasi-electron, but that lowers the degree. Quasi-hole increases the degree, quasi-electron lowers the degree. So putting a pair in doesn't change the degree of the wave function.
Right, okay, so in the case of the sphere where the droplet is all over the sphere,
yeah.
It doesn't do anything. But if I say it in the disk, for example, I put a flux of quantum in the center of the disk, the fact that I'm enlarging the degree of my polynomial
means the droplet will expand.
That it goes from a disk to an annulus, right? So
Yeah, that's right. The droplet size will expand. And so on the disk, it looks like an edge excitation. You insert a quasi-hole in the buck, you push charge to the edge.
Okay.
Whereas here, I put in a quasi-hole there, and at the South Pole, I'll be putting in a quasi-electron, right? Because I created them in pairs. So because whenever I ran at the North Pole, you'll see that all the directions are reversed in the South Pole, so that if the current came out this way here, it's going to come into this place here. Okay? So this is the state I've ended up with once I have threaded one flux quantum through the system. Okay, so why is this one flux quantum special? Well, it turns out that the Aharonov-Bohm phase picked up by electrons when they see a flux quantum. So this is the Aharonov-Bohm phase. The extra Aharonov-Bohm phase picked up because of my inserting this extra flux quantum through the system. This ends up being just one. Okay? So because of the Aharonov-Bohm effect, you know that the an electron going around a flux picks up a phase, right? That is the Aharonov-Bohm effect. And this phase ends up being just +1. So it's effect, this flux is invisible to the electrons in that they can't detect it in their motion. Okay, and there's another way to say this, which is that if I looked at the problem with this radial magnetic field and this extra flux quantum threading this way, I can do a gauge transformation, which brings it back to the problem with the radial magnetic field and without the flux tube. So these two are related by gauge transformation, which means they're the same physical problem. Okay, so what I've done is by threading one flux quantum, I have at phi is equal to 0 and phi is equal to phi naught, I've come back to the same physical system, identical physical system. But I've ended up in a new state, right? So what exactly does this mean? If I ended up in the same physical system, the ground state is the same. What we understand this as is that because this physical system is the same, and because we were adiabatically following a particular state, which is a ground state, this must be an excited state of the original system. Okay? So if, in terms of the energy spectrum, maybe that picture will help. Where's this phi? I have the energy spectrum at 0. This is the energy spectrum of the Laughlin droplet on the sphere. I had a unique ground state, and I have lots of excitations in a spectrum. Okay, in this spectrum, somewhere in here is a state which has a nu E charge on the north pole and minus nu E charge on the south pole. That's some excitation of my original system, and it has total charge 0. So yeah, it's allowed. It has these two excitations, but it costs energy above the ground state. Then what I did was I changed phi uniformly, or I changed it in time slowly until I got to phi naught, which I argued to you looks the same as phi is equal to 0. So that means I'm back here to the ground state. Okay, but what happens is when I try to follow this state along, I actually end up at this excited state here. Yeah, does everyone see this? So I start with the ground state at phi is equals 0. Adiabatically following it along gives me an excited state of the same physical problem. So thus, hopefully I've argued to you that the excited state of this Laughlin state there is an excited state in there with one quasi-hole and one quasi-electron. And further, this construction tells us that the presence of a quasi-hole or quasi-electron is associated with a flux. So remember, there's still a flux tube here, which is equal to phi naught here. So the composite excitation now is this blob. This is now our quasi-hole, UH. It has charge E over m, but it contains flux, which is phi naught. So this is some composite object. We think of it as both a source of magnetic field, so it has this phi naught magnetic field, but also has charge, which is E over m. Okay, so it's this weird composite object to be compared with an electron, which just has charge, doesn't bind, is not a source of magnetic field to further. Okay. Okay, I'll say the last bit really quickly. Why is this now an anion? So an anion is defined by the fact that it's really a property of exchange statistics. So if you had two electrons, what do we mean by the fact that they're fermions? We know that when we take they're identical particles, so when we do this exchange, we turn one around the other, this is the negative, picks up a negative sign from the original wave function. Right? That's the anti-symmetrization that we talked about, this is what we mean by an electron. Taking one around the other through a half circle picks up a minus sign. Taking around a full circle is just a plus sign, right? 2 times. An anion is one in which when you take an anion, mark it with an X, around another anion, you don't pick up -1, but you actually pick up a phase, which is e to the I. No, I guess it's 2 pi over q times the original wave function. Okay? So anionic statistics can exist in 2D. Why can they exist in 2D? Because in 2D, you see that exchanging particles is associated with a winding number, right? So if I have a particle here and one there, the number of times I take this around that, that's a winding number, and I cannot change this number at all by deforming the path in any which way I want. Changing the path continuously cannot change this quantized number, which is how many times did I take one particle around the other, right? So in a boson or a fermion, you know that you take it around once, you come back to, the wave function comes back to itself. In an anion, you take it around, I think, q minus, you need to take it around q times for it to come back to itself. Q exchanges are necessary before a system comes back to itself. Yeah?
Something that's still not understand with this whole business of the anionic statistics in 2D. We began with a system that is 3D, right?
Yeah, no.
I mean, the fractional quantum
Sure.
system is 3D. You said before that experimentally there have been like signatures of having anionic excitations, right? For the fractional quantum Hall effect.
You have seen the fractional charge has been seen. The statistics has not yet been seen.
Okay.
Yeah,
Right.
yeah. And it's important indeed for the statistics that the sample be pretty two-dimensional. If it's three-dimensional, because it does have finite thickness, and there's a third dimension through which these particles can escape, you see this winding number is not defined, right? And once this winding number is not defined, anionic statistics is not defined. So it's really just a special property of 2D that there's an extra number characterizing trajectories of one particle around the other, which is how many times did you go around, right? And that allows for the possibilities of multiple kinds of particles, not just bosons and fermions, but anions, which under one exchange pick up a phase e to the I 2 pi over q. Q is an integer. So q is equal to 1 is the boson, q is equal to 2 is the fermion, q bigger than that is the...
Should be pi over q, right? If q is 1, then you'll have an I cluster phase.
No, if q is 1, it's e to the I 2 pi. That's the boson.
Oh, yeah.
Q is equal to 2 e to the I pi, fermion. Okay? And q is 3 and above, anion. And anion is any ion. Anyway, whatever. It's just that it can pick up any phase. So our funny excitation here is an anion in that sense. Okay? And I'll just tell you, I'm not going to derive. There's a really nice paper by Dan Arovis and Frank Wilczek from the 80s where they use the wave function that we wrote down and derive these statistics. I'm not going to do that. I'm just going to show you why it comes about. So let's just imagine our picture. Oh, man. OK, I'll finish in just one moment. So our picture of the excitation is that it has charge E over m and binds a flux phi naught. Now I have one more of this object here. And I'm imagining taking one around the other. Okay? When I do that, you see that there are two contributions to the phase. The first contribution to the phase is the regular Aronow-Bohm phase, having to do with the fact that there is a magnetic field piercing this entire circle, right? So I mean, remember, these things exist in my electronic fluid with the strong magnetic field. So when I take this guy around some circle, I will sense the full magnetic field that's in there. And so that gives me a phase which is boring. And is the regular Aronoff-Bohm phase equal to 2 pi times the flux in the dashed circle there. Q star over E, okay? Q star is E over M. So this is charge times magnetic field, suitably, the units suitably picked. And so this is just a phase, and you'll see it's proportional to the area of this circle as it should be. Okay, however, there is a second phase, which is not the regular charge moving around a magnetic field picks up an Aronoff-Bohm phase, and this is associated with the fact that with the exchange statistics. So I'll just call exchange phase. Okay, and to see that there's a second contribution to the phase, note that this, if instead of keeping this one fixed and drawing the trajectory of this in time, if I move to the frame of reference of this particle, it will look to me like this particle is going around, right? And so if this particle is going around that one, this charge senses this magnetic flux. Does everyone see that? So the first phase was this charge sensing the entire magnetic flux. The second one is this charge sensing this magnetic flux. That is associated with exchange phase, and that ends up being 2 pi phi naught over phi naught, because BA is now phi naught, times Q star over E, 2 pi over M. Okay? So this is the origin of anionic statistics in these particles. They are a source of magnetic field, and so when one goes around the other, the fractional charge of one along with the magnetic field created by the other has an extra phase that is not that of a boson or a fermion, but an anion. So yeah, I'll just leave it at that. Thanks. Sorry for going over.
I'd like to thank Anusha once again for this course, and the gift present in the form of this shirt. I wish her all the best.